Hi, this is Joseph Dan again. Let's go through the pre-processing steps now. Okay, after that we have a generated mesh from SMS. First thing you probably want to do is load the DEM, right? So inside the directory 6B, I uploaded to the web. You can find subdirectory called DEM. So that's where the Gapco DEM, and also I downloaded the Tsunami DEM for Guam. Okay, so this is a demo. Most of the rest of them are the Gapcos. So inside that directory, there's a simple Perl script, basically drives the Fortran script. So this is the heavy lifting done by the Fortran script called interpolate depths. So it's basically interpolate depths and each load of H grid GR3 from this background raster, which is a structure grid. So that's a fast process. So this is a list of DEMs, Gapco, and so the order matters because they later you load the DEM. If there are overlaps between the DEM, then the value from the later loaded DEM will prevail, right? And in addition, you can also adjust the datum, right? So right now we don't because we assume everything is in mean sea level. And you can impose the minimum depths because the Gapco has a relatively coarser resolution. We impose the minimum depth of 5 meters, but for the Guam, we didn't impose any minimum depths. So the depths can be negative. So you can have inundation there. So after you get the a 2DM mesh, you convert into GR3 and it looks like this, right? All depths are 0. So you basically uh, change this to H grid old and then just launch this node DM. That's it. Okay, so I won't go through there. This relatively fast process. So that's how you get the H grid GR3 or hgrid.ll, which are the same in this case because we run the simulation in non-net coordinates. So hgrid.ll and GR3, they are the same thing. So next step is to generate the vgrid, right? So going to the vgrid subdirectory, there's a Fortran script. There's only one Fortran script inside. So that's the script that I briefly talked about, generating the LSS square. So you don't need to do anything. You just compile. If you use a Intel compiler, just copy paste this, right? And then just run this script and say, yes, you want to have a transect. I already prepared the transect from deep ocean all the way into the shallow region. So you can just use that. It's called transect.bp. So after this is done, you can use MATLAB script, is plot VQS, to visualize the master grid and the final transect grid. See how it looks like. So let's prepare that in the MATLAB now. Go into that directory, paste. Okay. So after this run is done, we can directly launch the MATLAB script. So it's relatively large grid, so it takes a little bit longer time. And many of those pre-processed scripts can be parallelized. You can, but vgrade should be the first thing you do because a lot of other scripts like the initial conditions and the boundary condition margin, they all depend on vgrade. Okay, so this is the first thing you do. So average number of layers in this domain is 34, almost 35 levels. That's understandable because most part of this domain is deep ocean. Okay, so now you can directly launch this MATLAB script. You plot out the master grid on top. Okay, so this is master grid from shallow all the way to the 10,000 meters. And this is how the transit grid looks like. You can zoom in. You can see that the surface is well resolved, right? The bottom is somewhat resolved, something like that. Okay, so now let's go to the next step. After this one will generate vgrid.in, right? So vgrid.in is here. So you just move to the parent directory. And the next, I just want to quickly show you the GR3, all those ASCII, simple ASCII files. But before that, I'd like to talk a little bit about some other inputs that are needed for the pre-processing, meaning the HiCon and the SFlux, right? The atmospheric things. So fortunately, Dan and other and Wei already prepare those files for us. So later on, I will talk a little bit detail about how to process the HiCon script. So those are from HiCon directly. Okay, structure grid and the SFlux is already processed by Dan. So sweet air and the RAND and the PRC are all there. So assuming that we have those ingredients ready, so next we can easily generate rest of the GR3 and the PROP, because they most of them are constant with exception of Shapiro. Okay, so this is the H grade. So you basically go to the evaluate. So depth equals 0.1, and then so that means all the depths and the entire grid is constant 0.1, and then you save it as albedo TR3. Okay, I won't do that because I override that. And then go to, I change the depth to 1, accept. So now if you go to display the isolines of eddy grid bathymetry, you'll see that everything is 1. Minimum and maximum both are 1. So you save this as diff max is maximum diffusivity. Okay, accept. Okay, I don't want to accept because it will ask me if I want to override the existing one. Of course, I don't want. Okay, and the 10 to minus 6, that's diff mean. Accept. Okay, and let's see what the others. I think it's a drag. Yeah. So drag is constant to start simple. So change it to drag. Right. Accept. No. And then put a 0. Right. This is a legacy input. Wind rotation angle input. Accept. No. Of course. So water type, that's the last one. It's 1. Accept, and then save as water type. Okay, so this is the type of the water. And that's about everything. Rest of them are spatially variable. So now let's go to proceed to generate the PROP. So you basically go to special property and make sure property and elements, right? Because element centered. So you initialize everything as 1 because we want to use higher order transport everywhere. We have other controls to switch to lower order inside param.nml. So to keep it simple, we just initialize everything to be 1, higher order, and then write tvd.prop. Okay, except of course I don't want to overwrite. That's it. That's everything ASCII. The other ASCII file you need is a Shapiro. So go into Shapiro subfolder. There's a Fortran script. It's a relatively simple. You can read through. Basically, it penalizes the steep slope with larger viscosity. That's what this is the formula. Okay, the viscosity is a function of a bottom slope. So you compile it and run it, and you ask you. So right now our grid is in non-land. You just say 2, and the reference is 0.05 and minimum 0.6. What this means is there's a hyperbolic time function. Okay, so you need to have a reference slope where at which the filter strength viscosity will increase. A minimum slope, that means below, if the local slope is smaller than this value, then there's no viscosity. Okay, just return. So now let's get ready to read in the output. It's called Shapiro, the slope filter.gr3, that's the output. So you can find the name inside this Fortran script, right? So now you can read this in as edit grid. So now go to the ISO line, look at how it looks like. So minimum is 0, maximum is 0.5. That's for sure. The Shapiro filter strength maximum is 0.5. So accept, and then it looks like this. Basically, you have larger filter and a steeper slope. You can see those scarps where the filter or viscosity really picks up. In the shallow, it's 0. Okay, and trenches also, you have larger slope and the viscosity. So that's what it looks like. But if you, since we already added a very high resolution near Guam, right? So we want to locally increase the viscosity there. Okay, so it's already pretty high, so that's good. So it's already close. So in this case, you probably don't need to do anything. If you want to locally in a non-AD region, you want to maximize the viscosity, you can create a region and set everything to be 0.5 maximum, right? So for example, you can create a region. I already created this Guam region. Yeah, so that's the Guam region. So this is basically, I use isobus as guide. So this is all the actual region. So inside this should be 0.5. So right now it's already 0.5. Okay, so you probably don't need to do anything. So just leave it. So that's your final, just move this to Shapiro. Yeah, that's it. I don't want to do this because I don't want to overwrite. Okay, slope filter.gr3, that's basically your Shapiro.gr3. So now let's go to the generate the initial and boundary condition from HiCon. So there's a HiCon. So this is directly downloaded from HiCon and processed there, and then go to hot and 3DTH. So there's only one F90 file. So just generate this, compile this file. You don't need to change anything, right? Compile it and run it basically. I don't want to, well, why not just let it run? So it'll take about 1 hour, okay, to do the 3D interpolation over 40 days. So it takes a while, but eventually you will generate the hotstar.nc and all the th.nc, ELIF, UV, 3D, all those kind of things. Those are the boundary conditions, subtitle boundary conditions for our 3D model, okay? So one thing I should mention is that we have 3 boundaries, open boundaries for this domain. Okay, so 3. First is Indian Ocean, Pacific Ocean, and Arctic. collection to the Arctic. So 3 open boundaries. So we need to generate tides for and the lodging files and those 3 boundaries. Okay, I'll show you how to do that. Okay, so first of all, the initial and boundary conditions running, and we can also in the same time do the lodging. Okay, so lodging has 2 Fortran files. One of them generates the GR3 file. So basically specifies a lodging zone. Another one generates the actual lodging file. That's CDF output. So let's first run the simpler one. This is a very simple script to generate the GR3, lodging GR3 charging zone. So just run it. So it asks you how many input number of open boundary segments, right? We have 3 open boundary segments, and then 1, 2, and 3, right? You want the lodging input for all 3 open boundaries, right? And then you ask you for basically what this Fortran script does is that you will create a lodging zone based on the vertical distance from the open boundary. So remember, everything now is in long net, so 0.8 degrees, right? That's the maximum distance from the open boundary. So roughly translate to about 80 kilometers. Yeah. And maximum lodging strength is 1 day because high count comes every day. So this one will generate all the GR3 file, just one nudge.gr3. I show you what it looks like. It's a bit slow. Okay, so now we have this nudge.gr3. Let's visualize it. Okay, go to the ISO lines. You can see nudging's relaxation parameters is usually very small. So you need to jack up the precision and auto scale accept, and then look at the so mostly a bunch of zeros in the interior, and closer to the 3 open boundaries, you have non-zero values, right? So let's get rid of this region we created before. Okay, so that's how it looks like. And second stage is to run this another Fortran script. We compiled and run again. Don't need to change anything. Just run it. So here are the inputs needed. Okay, basically high count thing, and the another ASCII input driver is this. Basically, you specify the temperature salinity. If it happen to be outside the high count grid, what we want to do, and the time step in high count is 864,100. That's 1 day, basically seconds. Okay, and you want to output every high count time steps. So keep the daily interval. Okay, So after that, you just run this. Okay, you'll take another probably less than 1 hour, but take a while. Okay, let it run in the background. So after that, you should get all the login files. Basically, that's this. The sol large and the temp large. Those two will be generated by the after the program is done. Okay, whereas the script we launched before, the inside hard 3D will generate the temp 3D, there's a boundary condition, and sol 3D, and also hard star.nc. Where's hard star.nc? Yeah, this one. So that's about everything except for we still need to generate the BC types.in, right? BC types.in consists of mostly boundary condition flags, right? The first part is the Earth tidal potential. You don't need to change anything except if your starting date is different, you need to update the nodal factor and arguments. Okay, same for here, the boundary forcings. We use 8 constituents from the FAS. So I'll show you how to generate the FAS boundary condition. Again, we use 3 open boundaries. So this is the first open boundary, and you use temporally and spatially varying temperature salinity. So that's the 3D.th.nc, right? That's generated by the HiCom scripts. And for elevation and velocity, we use type 5, which is basically combination of a tidal and subtidal. Subtidal from HiCom, that's the one we are generating now. But for the tidal part, we use FAS. So that's basically, the FAS basically generate all those numbers for you. Okay, all the way after that, this is a elevation. So you have amplitude and phase for elevation, right? And this after elevation is listed, you have also the velocity component u and v, amplitude for u and amplitude for v here, and phase here. Okay, so that's the last one basically related to the temperature and salinity nudging the relaxation constant when they are incoming. Okay, so I'll show you how to generate the amplitude and phase using FAS. Okay, so first of all, let's go to the FAS directory right here. So there's a README inside the FAS. So I already uploaded FAS 2014 to the website. So you can have the entire package I have. So the main MATLAB script is this. So if you look at header, it will tell you how to use this. First of all, you do generate list of open boundary longitude and latitude. We have 3 segments now, right? And to do that, you need to use this simple Fortran script. Okay. And this one is part of FAS, you don't need to worry about, and iflag you don't need to worry about. We always generate the elevation and the velocity. So mostly you need to generate the those 3 inputs, the foreground BP dot 1, 2, and 3, for 3 open boundary segments, right? How do you do that? You go to this Fortran script. You take hgrid.ll or gr3, right? In our case, they are the same, and prepare this simple ASCII input. This ASCII input, first line, specify number of open boundary segments. In our case, 3 open boundary segments, and the first, second, and third, right? It's basically list out all the open boundary segments in your hgrid.gr3, and that's it. So we just need to link this to hgrid Pacific B, right? We just link it. Now hgrid GR3 is point to this mesh we used for the Pacific. So now you just compile that and run it. You generate 3. Actually, your num or FP, the foreground.bp, you have 1,336 points because this is a combination of 3 segments. So it's you need to basically break them into 3 segments. 1, okay. I have some old files there, better remove. Okay. 2 and 3. So now let's see how many we have. The first open boundary we have 395. So 395 plus 395. So delete this. Yep. So this is the first open boundary. So these are long-land coordinates. And get ready for 395. End of this. So D1G. And the second open boundary you have 899. Okay, 899. Right. So this is the end of the second. So save it. And the third, basically 399, 395 plus 899. Okay, so this is basically the last one. Last one should have a 42. So just verify that. Last one should have 42. That's Arctic. Yeah, 42 exactly. Okay, now you have 3 inputs ready, right? So they are ready. So these 3 inputs are ready. So just go ahead and launch this MATLAB script. You generate the 3 files for you, the ap.dat.123. So those are the numbers you need. Okay. While it's running, I think that's basically all the steps you need. The only thing we haven't covered is how to generate the high con and the S-flux atmospheric. So Dan prepared 2 simple slides. Again, we won't go into the detail, but if you have questions, feel free to ask Dan. You know, you probably have your own favorite tool to convert those products into our format, but Dan, you mostly likes to use NCL and uncall command. So you basically use uncall command to download the OpenDAP HiCom product. Get them. Yeah, you basically download from the OpenDAP thread, HiCom, and then you need to use NCK kitchen sink. Basically convert them into daily format, and then correct. You need to use convert those numbers into our CF conventions. Specifically, the temperature originally is in situ. We need to convert them into the potential. So to do that, you just use this one-liner, CDO command, and then you need to concatenate them into stacks. And finally, you use this output, UV underscore, TS underscore, and S underscore as input into our Fortran script. And to prepare atmospheric files, there are many different types of products, so we have scripts for each product. So for example, what is shown here is the dance steps to convert ERA 5 into a SFlux. So you basically go there, download using Python in this case, yeah. And then basically you use NCL again to convert the some variables, and finally use this Fortran script to produce the sflux. So there are lots of details. I won't go into detail, but feel free to ask questions to them. Okay, so now the MATLAB script is done. So let's take a look. So you can see 3 AP, the amplitude phase that are 1, 2, 3. So it's basically in orders already. All right. And this is the first part is elevation. The second part is the velocity. So now we just move to this directory and go back to this directory, and yeah. Okay, let's go. So suppose you don't have anything to start with, right? DG, so like this. So the second one is 899, that's Pacific, 5544, same flags. That's last one, 42 is same flag, that's Arctic. And don't forget, because you specify the temperature salinity boundary condition, so you need to have a relaxation constant in the end. Just before you forget, just put there first. And then now you put 1 first. So this is you're already in order. So we follow the FS order for the constituents, right? S2 followed by M2. If you go to next one, should be M2. Yep, it's M2. Yep. And go to Pacific, and then append the second, and go to Arctic, and append third. That's it. So this is your BC type start in. Okay. With that, after the Fortran script, the two Fortran script for initial condition, boundary condition, and margin are done, you are all set. So all the inputs are there already, right? Yeah, for this case, we just use constant drag. Let me see. Yep. Okay. Hopefully you can reproduce my steps. Thank you.